Hello there, Energy students. Welcome back. I want to talk a little bit about the kinds of regression lines or best fit lines that we've been seeing so far in this module and how we can make them more interesting, if not better. We'll see how that sometimes they're better and sometimes they're worse. But everything we've seen so far in this class, and probably any place you've seen any kind of like best fit lines in your education, has been just that. It's been a line. It's been a linear relationship that we're using to build a statistical model between two random variables, an x and a y. Words like statistical model and random variables might not have been words you were using in the past when you had these ideas, but that's what they were. Alright, so if we have these basic ideas, okay, for a linear fit like what I'm seeing here, that doesn't look so bad. But what if my data looks something like this? For example, I got kind of this arch-shaped cloud of data here. For example, maybe the data here are on the x-axis is maybe time of day, and the y-axis is maybe like power being produced by my solar panel. So like, at first early in the day, the amount of solar power being produced is not very large, and then over the course of the day it got larger and larger, and then after noon it started going back down. Well, we could certainly take those ordered pairs, those paired data of x's and y's, and we could compute a linear regression model using the polyfit command, the way we've seen before, and we could actually come up with a model where our estimates of yi hat, are equal to some some b naught plus b1 times our values of x, like xi, and actually for a data set that looked like this, that really wouldn't actually make much of a correlation. I mean, you could always compute a regression line like this or a best fit line, but it wouldn't actually have a very high correlation at all. That line that I just drew in there, sketching it in, doesn't really explain very much variance going on in that data set, right? Any value of x, if you go up to the best fit line and then read out the value of y, they're generally terrible forecasts, right? So I think we can do better than that. Well, one thing we could do is come up with a model that had a second order term in it, where like we're simulating the process as being, or we are building a statistical model here where the process is actually quadratic. It's a parabola. And so here's our model with a second order term where now we have our forecast y of I hat, where we're looking for the ith observation of y. We're trying to estimate we're trying to estimate the ith observation of y. And then we have this quadratic equation on the right-hand side. b naught plus b1 times x of I plus b2 times x of I squared. So it's a little quadratic equation here, and in this case, this is going to actually make a correlation that is significantly better than what we had before. We're now far away from zero. Now I wrote this there as little r, but strictly speaking that's not right. This actually is a different statistic that would be describing. Little r is the regular, what did your textbook call it? The ordinary or the Spearman correlation coefficient. Strictly speaking, once you start having these nonlinear type of best fit lines, then it becomes big R, where big R is called the coefficient of multiple correlation. It actually works more or less exactly like regular correlation coefficient, except regular correlation coefficient can go from -1 to 1. Big R, the coefficient of multiple correlation, actually only goes from 0 to 1. The reason why it has to do with the fact that there's no real sense to the sign when we're talking multiple correlation here. The sign of the ordinary correlation, little r, had to do with the sign of the slope of the best fit line, but once you start having a curve like this, there's no sense to the sign of the slope and things like that. So that multiple correlation coefficient, big R, doesn't have a sign. It just goes from 0 to 1. But other than that, it works exactly the same way. It has the same relationship to percent variance explained that ordinary correlation does. Now, something astonishing happens when you make another term that to add to your regression model, like when we moved up to the x squared term here. When you add that quadratic term, I absolutely 100% guarantee to you, your new big R, your new correlation coefficient of multiple correlation for this new equation that has a squared term in it will be bigger than the absolute value of your old correlation was. It always will be. It will always explain more variance. It will always have a higher correlation. The correlation will go up no matter what, even if your data aren't really related in any kind of quadratic way. Oh, well, that just has to do with the numbers of the whole thing, but you will be explaining more variance here. And for that matter, we can go ahead and do the, again, I mean, heck, if adding a squared term made things better, how about add a third order term? So now we have a new regression model that has a cubed term in it, where like our yi hat, what we're trying to estimate, has 4 terms on the right-hand side, b naught plus b1 times xi, plus b2 times xi squared, now time plus b3 xi cubed. Now, this b naught is not the same as the b naught in the quadratic form of the equation, which is not the same as the b naught in the linear form of the equation. And same with like b1 and stuff like that. You have to recompute them each time. You can't just keep adding more terms here. You have to recompute the b naught, the b1, and the b2 when you add it to b3. But it can be done, and Octave can do it in a fraction of a second. I mean, this is a very fast and easy calculation. Now, in this particular case, maybe it would turn out that that third order term is small, that beta 3, that b3 there, might be very close to 0 in this particular case, because this doesn't look like a third order, like a cubic spline or anything like that. It looks like a parabola. So probably that b naught would, that b3 would probably be pretty close to 0. But again, astonishingly, no matter what, the new coefficient of multiple correlation, big R, for this third order version of the equation will be better than the big R, the coefficient of multiple correlation, for the second order version. This correlation will get better by adding a cubed term to it, even if the data don't have anything to do with a cubed term. In fact, we can just keep playing this game over and over again. What about n terms? If we wanted to have an nth order term, I don't know, 7th order polynomial that is our model or whatever, 20th, it doesn't really matter. If you want to make a 20th order term, whatever, an nth order version of the equation, it'll just be y sub I hat, our estimate of y sub I, is equal to, and then on the right hand side it's just the sum, as I'm going to use my dummy variable j here. J goes from 0 to n of b of j times x of I to the jth power. Okay, it's just a little sum, like that little sum product, to use a terminology. And believe it or not, no matter what value we choose for n, we can always get the correlation better by going one bigger as to what order we want this this regression model to be, the statistical model to be. So if the coefficient of multiple correlation, this big R of our jth order polynomial, it will always be greater than the coefficient of multiple correlation for the j minus 1th order version of the equation. Adding more and more powers to the statistical model will always improve the correlation. Well, if that coefficient of multiple correlation, big R, if it goes from 0 to 1, does that mean that if I add enough terms to this equation, that R will eventually reach 1? Yes. You can eventually add enough terms to this equation that you get a perfect fit. You're not going to like that fit, but you can add it. I mean, with enough terms, your best fit line basically just becomes a dot to dot. It'll literally be a polynomial that's graph is just connecting the dots of your data points. Okay? Your statistical model is now perfect. It has a correlation of 1. On the other hand, I don't think that's really what you want to do. I mean, if your data set has 600 and some thousand points or something, let's say, do you really want to have terms in your statistical model like x to the 600,000th power? Probably not. Probably that has lots of reasons why that would not be the best choice there. Let me give you another example of how this is maybe not such a great idea. Let's say you have this data set here with these 12 data pairs, okay? And I'm not happy with this data, okay, that I've drawn here. Notice how it kind of falls into 3 little clusters like this. each with 4 points in it. They're not very evenly distributed across the x-axis or the y-axis. There's lots of problems with this data set that a statistician would look at this and say, I don't know that correlation is the right tool, and best fit lines and stuff like that are the best tool here at all. But if I wanted to, I could certainly use the polyfit command and come up with a linear fit to this data. And, you know, it might look something like the line I have sketched on here. And this is my first order version of the equation, where the highest power of x of I is just 1. And so we just have a b0 and a b1 term in our equation here. And, oh, I don't know. I mean, I don't know that I think that that line that I just drew in there looks all that exciting. It doesn't seem like it fits the points very well. It doesn't seem like this would be making good forecasts. Let's try putting in a second order term. So we would recompute and make a new statistical model with a b0, b1, and b2 term in it, where we go as high as the second order. We have an x of I that has a squared in it, and we would get a parabola that maybe looks something like this. And well, maybe that's not bad. I don't know. That would have a certain value of big R, the coefficient of multiple correlation, and it would be better than it was for that first order equation where we just had a line. Well, if second order was better than first order, let's try third order. And let's say we drew a third order regression line through the data and we got something that looks like this. Okay, wow, that goes right through each of those little clusters of points there. And you know what? That probably has a really high coefficient of multiple correlation. Probably getting pretty close to 1 here. Wow, hey, this is great. We should definitely use this as our model of whatever it is we're trying to make a statistical model of. Except no. See, in this case here, I don't think I like this statistical model here at all. I mean, do we really have any reason to think that a value of x along, you know, as my independent variable at like this location along the x-axis in any way corresponds to this value of y way up here? I mean, there's nothing about the data that suggests that there are any values up that high, much less values of y that high between those two clusters of points that were earlier. This doesn't really seem like that model tells us anything meaningful about what's going on in the data. In this particular case, I don't know that I think best fit lines are the best choice of a way to be making a statistical model here. But we'll see other tools that can do this better perhaps later in the semester. So even though that first order model might have been kind of boring, and didn't really fit the points all that great, it seems to be the most consistent with what the data is actually telling us. I mean, that first order model shows us that, well, the x values range over this range, and the y values range over that range, and that's basically all we know. Okay, so that first order model may not have been the sexiest, but it definitely was consistent with what the data was telling us. Yes, we could make a model that had even higher correlation, but it just wasn't really telling us much of anything about what the data actually said. I mean, there's a property here that we want. See, it's a trap. We can always add more and more terms to our regression equation, our best fit line equation, and the more and more terms we add, the higher powers we're going to get of x of I. Yeah, correlation coefficient is going to go up. It is guaranteed. The math of it works out so that the correlation coefficient always goes up when you add more terms. But do those terms actually mean anything? I mean, is there any significance to the x to the 27th power term in your equation? No. You want to work with as few terms. You want your statistical model to have as few terms as possible, but still produce useful estimates and explain a lot of variance in your data set. And there's a word for that. Kind of a strange word. In statistics, we have a value, as in like something we hold near and dear to our hearts, called parsimony. If you pull out your dictionary and look up the word parsimony, it's going to tell you it means something like stinginess. Okay? That's one definition of the word parsimony. In general, though, it means, yeah, kind of like, I'm only going to do this if I absolutely have to. You want your model to have as few terms as absolutely possible. Yeah, I can get a little bit better correlation if I add another whole dumb term to it, but I don't want to spend that much work. Okay? I want to find the version of the equation that has as few terms as possible, but still tells me what I need to know about the process at work. I want to be as parsimonious as possible, as stingy as possible. This is a real value in statistics. When you produce a model They don't want to include lots and lots of terms that don't actually, yes, you add more and more terms, the correlation will get better, but was it worth it? I mean, you did a whole bunch more math to make this happen, and your model may be telling you things about, I mean, the curve that you're producing may be all over the scatter plot. Does it actually tell you anything useful about what's going on in the data? You want your model to be as parsimonious as possible. You want your model to exhibit parsimony. In other words, you want it to have as few terms as possible, even though giving it more terms will raise the correlation. All right, so great. We now understand that we could make curves. In practice, we're mostly going to want to make just linear best fit lines. Maybe quadratic. Maybe there are processes that, like describing them in terms of a parabola could be useful. But I'm going to steer clear. I mean, in general, we're not going to get into third order, fourth order, fifth order, unless there's some reason to think that's necessary. So where are we going to get these terms? How are we going to actually in Octave get these B0, B1, B2, etc.? And it turns out that's what that polyfit command can do. Remember, back when we were first learning and reviewing about correlation, we learned about this polyfit command, where if you have two columns of data, I'll call them X and Y, and they have rows that contain values. They're each one column wide and a whole bunch of rows long, but the same number of rows long, so they're pairs of data. Then before, when we were doing linear fits, we were just putting a 1 after there. But now we can put higher order numbers. We can put something like 3 to make a third order polynomial fit through the data. Now, that's the right-hand side of the equation. The results will get put into the left-hand side of the equation, which I right now have put as a variable called b, but b will be created and become whatever the order of our equation is. It'll be that plus 1. Now, I have no idea why Octave does it this way, but it puts the coefficients in backward. So like, for example, after you've run this polyfit command to get the third order polynomial, so you have just computed B0, B1, B2, and B3, it actually puts them in the opposite order in this B array. So like the value in your variable B parenthesis 1 is B3. And the value that's in this B parenthesis 2 well, that happens to be B2. B parenthesis 3, the third value, the third column of the first row of B is actually B1. And B parenthesis 4, the fourth column of row 1, is B0. That is just so confusing. I have no idea. There must be some reason as to why it's done that way, but that is just confusing and not useful for how we're going to be doing it. So I have a better plan for you. We're going to introduce one more little command in here, but you're going to be grateful for this. You still use our polyfit command where we're doing a third order best fit to the data in the pairs of data in X and Y, just like we did before, but let's stuff it into a different variable with a different name. I just tried like btemp for like temporary or something like that, okay? So it'll compute, polyfit will compute all of these B0, B1, B2 terms, and it'll stuff them into this new array btemp. Then there's a little command here that is called fliplr. Fliplr takes an array and just reverses the order of it. So fliplr stands for flip left right. There's also a flip up down, but this is flip left right. And it'll take those values and reverse them. Now I put that into a new array called b. Okay, this is less confusing because then b parenthesis 1, well, that's your B0 term. And b parenthesis 2, that's your B1 term. Oh my gosh. All right, and so on farther and farther down. B parenthesis 3, that's your B2 term. This is the best we can get it. It would be better if Octave had a 0 array. Like, if there was a B parenthesis 0 in Octave. Most computer languages do have that. For whatever reason, Octave doesn't. Because then we could make B parenthesis 0 equal to B0, and B parenthesis 1 would then be B1, and that would be lovely, but for whatever odd reason, Octave doesn't have that built in. Alright, when we use this in the project, I will review it with you and help you a little bit on the step, because I recognize that this is awkward, how we have to get these values of B out of the polyfit command. All right. I don't really see any value here in asking any questions about this stuff at this time. I mean, in terms of like for me quizzing you. Obviously, if you have any questions, please let me know. Or this is the end of the lecture, just go back in blue line to the main page and move on to the next lecture. Let me know if you have any questions. This has been Dr. John Shiraki.